Let's start by taking questions from the homework. What questions do you have? Ellie?
I have a question. Class from Friday, is it?
The class from Friday. Did I have a video from Friday?
I think your computer was spazzing.
I'll have to see. If I had a video, I'd put it up. I thought I had posted something.
Which video?
On Friday. Was there a video for Friday? Okay. Yeah, it's up there. Derek, you had one you wanted to ask? Alright, let's look at 65 here. Guys, listen, these things especially, you've got to really make sure you're understanding as we learn them now. Okay, this is not the kind of stuff to zone out on. So really stay with me here. On 65, we're looking for a full house. Okay, if you're not familiar with cards, they explain what that is. Okay, a full house consists of 3 of one kind. Okay, so 3 3s, 3 8s, 3 kings, 3 10s, 3 of something. Alright, combined with 2 of something else. Okay, 2 of another. Now, one key here is that they've got to be different. Alright? Especially since you only have 4 of every type of card. You can't have 3 of a kind and then 2 of the same card. Okay, that would be 5. So 2 of a different card. Okay? So let's think about this with our combinations. First of all, how many different cards do you have to choose from? Not the whole deck, but
13.
Yeah, there's 13 in each suit. Okay? And we're going to choose one of those, right? So we're going to pick one of the 13 cards first of all, in order to be the one that we have 3 of a kind of. Okay? Now, how many of those do we need?
3.
3. How many are there available?
4.
4. Okay? So we have 4 available, and we need 3 out of the 4.
So you multiply those together.
And we multiply those 2 together. This is how many different ways you can get 3 of a kind. Okay? There's 13. 13 choose 1 is 13. 4 choose 3 is 4. So 13 times 4 is 52. There's 52 different ways you can get 3 of a kind.
I thought you'd see the factorial.
Well, yeah, you'd use the formula. I just know these ones.
Isn't you to do 4 times 3 times 2?
Well, you would do, for 4 choose 3, you would do 4 factorial over 4 minus 3 factorial times 3 factorial. Okay? Well, that's just 1. This is 4 times 3 factorial, so that cancels that out, so you just have a 4. Okay? These two actually you can figure out logically. How many different ways can you pick one thing out of 13?
13.
13, okay? How many different ways can you pick 3 out of 4? Think of it this way. How many different ways can you pick 1 to leave out?
4.
4, okay? So, if you're picking all but 1, it's the same as picking 1. Alright? So like if I had 13 choose 12, how many ways could I pick 12? 13 different ways, because that's the same as picking 1 to leave out, you're picking 12 to include. So you get the same number either way. Alright, now it's not the same with permutations, but combinations.
Do we put the card back after we pick?
No, you're picking 5 total, okay? If you put the card back, you can't use combinations, okay? You can't use combinations or permutations if you're replacing every time, okay?
But we choose 1 out of 13 first, and then there are 3 left, and we need to choose 2 of it.
Well, no, I get what you're saying. If we already have one in our hand, then there's only 3 left in the deck, and we're picking 2 of those 3.
Yeah.
What this is all happening simultaneously. So all 4 are in the deck. You're picking 1 out of the 13, and you need 3 out of the 4. So I'm getting them all. It's not like I take 1 out and then and then it changes for the next part. Okay. So. All right. Yes.
Is number 66 just 1?
Well, hang on. Let's do this real quick. Okay. 2 of a different card. We had 13 to choose from before. We don't want the same one, so now it's 12. We're going to pick one of the remaining 12. Okay, so if we picked an 8 first, then we have 3 8s. We can pick ace through 7 or 9 through king. We can't pick the 8 again. So it's 12 choose 1, and now it's 4 choose 2, because we want 2 of a kind. So that's 12 times 4 choose 2 is 6. Okay, so 12 times 6 is 72. So here's where our fundamental counting principle comes in. If there are 52 ways to get 3 of a kind, and there's 72 ways to get 2 of a kind, then 52 times 72 is the number of ways to get 3 of a kind and 2 of a kind. Okay? So you get, I think it was 3774. Is that right?
3744.
3744. Okay, I knew there was a 3, 7, and a 4 in there. Okay. Does that make sense? Kinda?
Oh, does the color matter? Like the space?
Well, it only matters, we're taking care of that part when we're doing the 4 choose 3. Because you have the ace, or the hearts, diamonds, clubs, and spades, those 4 to choose from. So you could have diamonds, hearts, and spades, or clubs, hearts, and diamonds, or that's what you're figuring out when you're doing this part and when you're doing this part. Okay?
So the 13 represents the 4.
There are 13 cards in
Fours,
each
yeah.
suit.
13 fours, yeah.
Mm-hmm.
We choose
So-
only one of them.
Alright, now let's see. 5 cards are chosen from a standard deck of 52 cards. How many 5-card combinations contain 2 jacks and 3 aces? Okay. If it. Well, here's the thing. 2 jacks, we need 2 of the 4 jacks, right? So it'd be 4 choose 2. We need 3 out of the 4 aces. So it'd be 4 choose 3. So 6 times 4, there'd be 24 combinations that would give you 2 jacks and 3 aces. Or aces full of jacks. So that's how you say full house. Aces full of jacks. But, anyways. Any other questions on any of the homework? Okay. If you did not do these, you're behind. Okay? There's a lot of logic that you've got to work out and you've got to think through in order to be able to do these. Today we're going to start looking at probabilities, and part of figuring out the probability of something happening is figuring out how much it can happen and how much everything else can happen. So you have to be able to figure this stuff out in order to do any probabilities. For example, now that we know these 2 numbers, I could say, what's the probability that a full house is going to be aces full of jacks? Well, 24 out of the 3,744 possible full houses are going to be 3 aces and 2 jacks. Okay? But you can't figure out that probability until you can figure out the number of possible combinations. Okay? So, There's a lot going on here that we have to work through. All right? Final call for questions. All right. So, what I want to look at today is kind of an introduction to probability. We're doing section 8.7 in your book. 8.6 and 8.7, you might remember we skipped back when we did the binomial theorem, and we did sequences and series. So we're revisiting those, but we're also going to make this whole unit out of a number of different parts of your book and also some stuff that's not in your book. But basically when we're talking about probabilities, we're trying to answer the question of what are the chances that something is going to happen? Okay? What are the chances that whatever we're talking about is going to happen? Now, probabilities are used in a lot of different circumstances. They're used in calculating insurance costs. They're used in athletics. They're used in picking which route you're going to take to work. Okay? They're also used in a lot of other games and things like that. But probabilities, we actually, without even realizing it, use on a day-to-day basis just to make simple decisions. Which one of these strategies is going to give me the best possible chance for success? Okay? So, now, there are two different types of probabilities, okay, that we're going to talk about.
We're missing 4, right?
Okay, we're missing 4. I realized I forgot to take attendance.
Jacob and Yosh.
Jacob and Milosh are both in the band thing for the in rehearsal. So, all right, two different types of probabilities. One is empirical or experimental. Okay, this is an inductive process. It's an inductive process, meaning that we're going to look at a lot of events that happened in the past, and then we're going to try to use that probability for future events. Okay? Can someone give me an example of a case where you might look at what's happened in the past over and over and over again and try to use that to make a decision for the future?
Yeah, what are the chances a crash will occur on Lions Road?
Okay.
You just look
The
at
police could look at the
reports.
historical data. Okay. How many accidents have we had? How many can we expect in the future?
Yeah, so you can determine how many officers to put.
Okay. And then two, they can also use, kind of going along with that, they could say, okay, this city had a similar intersection or something that had a lot of trouble. Let's see how they fixed it. And then they can predict, hey, doing this will decrease it a certain amount.
Is this also like when you say, let's say a baseball player, like a hitter, if you say, if he hasn't hit for a couple of times, then maybe that means that he's gonna hit more often?
Okay. Yeah, and that's kind of using the idea of, and that kind of goes both ways.
Yeah.
He hasn't gotten a hit in a whole bunch of times, so does that mean he's not very good? So maybe we should have somebody else hit this time?
Yeah.
Or is he just about ready to come out of his slump and start hitting again? Yeah, it's used in baseball a whole lot. If you watch a game, towards the end of a game, you'll see them switch pitchers. You know, sometimes 3 batters in a row will face 3 different pitchers. Okay? And that's because historically, maybe that batter has faced this specific pitcher and hasn't gotten a hit on him in 10 at-bats. Alright, so they say, hey, this batter really struggles against this pitcher, so we're using that to say the probability of him getting a hit this time is very low. Okay? And it works in reverse as well. You know, you might pinch hit, you know, put a different hitter in for somebody if you really need a hit and you know that you have someone on your bench who does really well against a specific pitcher or maybe a specific kind of pitcher. And actually, analytics is using statistics and probabilities in sports and lots of other things too, but a lot of professional athletics teams use analytics to help them construct the best lineup for a particular game against a certain pitcher. The catcher and pitcher use it when they're calling, you know, what pitch to throw next. You know, this guy really struggles with high fastballs, so we're going to throw him a high fastball. That's empirical or experimental probabilities. Okay.
Is that what your brother does?
He kind of does that, yeah, with medical stuff. So, yep.
What about, can they calculate like LeBron statistics?
Well, here's the thing. In basketball, this is used like at the end of the game. If you're down, if you're down by like 1, you might try to foul the other team, so they have to take a free throw and can't run the timeout. So, yeah, so you foul the worst free throw shooter.
They're at least like
Okay. Or if a particular guy gets the ball and you know he's gonna score, but he's a terrible free throw shooter.
Yeah.
Like I don't know if you guys remember Shaquille
Shaq,
O'Neal.
yeah. Hack a Shaq. They call it hack a Shaq.
Yeah, hack a Shaq. That's what teams would do all the time.
They do it to Dwight Howard.
He was lucky to get 50% free throws.
Yeah.
But if he got the ball within 10 feet of the basket, he was gonna score because he was like 7'4" and 360 pounds or something like that. I mean, he was just massive.
How do you know foul someone that big?
They would just grab him and hang on. So, but that was, we need to keep moving, but that all is experimental probability, okay? I might drive a particular route to school because every time I've driven another route, I catch a bunch of red lights, but the times I've driven this route, I tend to get more green lights.
That's what my dad does.
You know, so there you're using probabilities. Okay? Yeah.
You see like Shaq's like Hall of Fame speech or like retirement speech. He's like, I'm gonna miss a lot of things. He selects three things. Free throws.
Yeah, free throws. He had one of the ugliest shots I've ever seen on free throws, but yeah. Oh yeah. Anyways, we are going to be using a lot of another kind of probability, and that's what's known as theoretical. Theoretical probability is more of a deductive approach. Okay? Inductive means we're taking a lot of data from the past and coming to a conclusion that we're going to try to project onto the future. Here, we're starting with certain given information, and we're trying to then apply it, okay, and be deductive. We're using a logical train of thought to calculate a probability. This would be like, for example, if we're throwing something at a target and it has a bullseye on the target, we could calculate the theoretical probability of hitting the bullseye by simply taking the area of the bullseye and dividing it by the area of the entire target. Okay? And if you want, you can even test to see, you know, how accurate would that end up being. With my younger geometry students, we would study on a basic level this theoretical probability, and we would get little guys with parachutes and we'd drop them from the balcony of the gym. And I'd have a target set up and we'd count, in that target we'd have little mini targets. So we'd count how many hit the landing zone or the main target and then how many hit the little ones. And they'd compare that experimental data to the areas divided by the total area. And it was kind of interesting. But that was for our geometry class, so it was a lot more about area. But anyways, so empirical and theoretical. Empirical is inductive, theoretical is deductive, okay? The last thing I want to look at is the concept of sample space, and we're going to spend a good amount of time talking about this sample space in an experiment, which an experiment is just a situation that we're working with probabilities in. Doesn't have to be a scientific experiment. Okay, but the sample space is all the possible outcomes in a certain circumstance or in an experiment. Okay? Each outcome of the experiment corresponds to exactly one element of the sample space. Okay, so you can't have more things in your sample space than you have possible outcomes. Okay? However, the number of elements in the sample space is not always the denominator of our formula for probability. Okay? It's not always the total of the possible ways we can get those outcomes, I should say. Okay? So in other words, there may be different permutations of events that give us an outcome, but the sample space is like all of the combinations of events. Okay? And you'll see that later. And there might be different circumstances where we want the order to matter or we don't. Okay? Well. Alright, so let's talk about getting a sample space for a problem. And let's say, for example, we're going to flip a coin 3 times. So we'll keep a simple concept for the moment. Okay? One way we can determine a sample space is by finding a tree diagram. Okay? In a tree diagram, what we do is we outline the possible results. So we're going to flip a coin 3 times. On the first flip, we could get heads or tails. On the second flip, we could get heads or tails, and on the third flip, we could get heads or tails. But if we're finding the sample space, we need to trace all the possible outcomes of the 3 flips. So, for example, we could get all heads. Okay? Or we could get 2 heads and a tails. But that can happen multiple ways. Okay? There's only one way to get all 3 heads. Okay? But watch this. We could get head, head, tail. Alright? 2 heads and a tails. Or, look at this. We could get head, tail, head. But we still got 2 heads and a tail, right? Okay? So there's 2 ways of doing that. There's one way of doing that.
There's a third way.
Yeah, there is. We're going through all of them here. So we could also get head, tail, tail. All right. So head and 2 tails. Okay. Then if we go down this branch, tail, head, head. 1 tails, 2 heads. There's another way of doing that. Okay. Or tail, head, tail. 2 tails and a head. There's another way of doing it. Okay? Tail, tail, head. We have another way of doing that. Or all 3 tails. Okay? All 3 tails. And there's only one way to do that. So, our sample space is a set. Okay? It's a set of possible outcomes, and those outcomes have to be unique, though. Okay, the outcomes have to be unique. And what we end up having here is the set of all unique things, but we also, once we start getting probabilities, we have to consider how many different ways could each of those outcomes occur. And that's where the counting principles that we learned last week will come into play. Okay?
So with these, the order doesn't matter.
On these, the order doesn't matter. There may be occasions, we're going to see one later, where the order does matter, but in this case, the order doesn't matter.
So it's a combination?
So it's a combination. Mm-hmm.
Can you go back to the slide before?
What do you need here?
The number of elements in the sample space.
It's not necessarily the denominator of our formula. And that's just the number That's the number of total possible outcomes.
I have a conceptual question for you.
What?
Okay, so you know how when you flip a coin, like every time you flip it, it's 50-50 no matter what?
Yes.
So you flip it like 3 times in a row, the next one's still 50-50?
Mm-hmm.
What if, so like, but like if I flipped it like 5 times in a row and it landed heads every time, and then asked you to bet on the next one, it's safe to say you bet tails, right? Just because.
Probably.
That's a really good question.
Okay, well, what if I flipped it like 1,000 times in a row and it landed tails every single time? Would you bet on tails the next time?
Well, that's the thing. That's where you have to start questioning, do you have a fair coin?
Yeah.
Yeah, tails on
Yes.
Or the way you're flipping it too, 'cause
Or-
sometimes if you're flipping it
That's a really
favoring
good
one
question.
side, that could also.
Yeah, if you flip
I'm
it,
dead serious.
like if you flick it with just the same amount of pressure every time, and it starts with the same side up every time, and you catch it at the same level, it's possible, if you practice it enough, to do it exactly the same way every time. Like if you have tails facing up, and you do it with the same amount of pressure every time, and catch it at the same level, theoretically you could kind of train it so that you got it.
You can win
To
money
work.
off that.
So that's why like in the NFL or whatever, when they do the coin flip, they just toss it up in the air and let it fall on the ground, so it might bounce or roll, and there's no chance of that
That's what
happening.
they do in soccer too.
So yeah, so there's a reason for all of that. So
So
yeah.
basically, like probability is just a fake.
What?
It's like fake, right? Because everything
You
is
said
about like
fake
gravity
or
and
fake?
stuff. So it's like nothing to do with probability, right?
Gosh.
No,
Like
it
seriously
does.
though. Like what you said, you know.
LeBron.
You're just
Actually, there is
I don't like
a-
the chapter 18.
You're just
I don't like
You'd have to
probability.
test it, but I think it's the $50. The $50, I think, because of the way it's designed, the face on it is so large on the
It's a
head
little
side,
more percentage
it's weighted a
heads.
little bit more, so it's more likely to land
On the toes.
Yeah,
tails.
I think it's
I
quarter.
think.
But does probability
But-
I
not,
read somewhere.
not
Anyways.
count for
Like a
like
penny is like.
all the other
that sounds
factors, like it
like-
could be windy, you know, like.
Well, here's the thing, guys,
Fake.
and this is the difference between theoretical
You can say math is fake.
and empirical probabilities. Guys, listen, okay? What you guys are talking about is developing a empirical probability. I flip it 1,000 times, I get heads every time, okay? Probably something's up with my coin, so the theoretical probability is 1 out of 2. But there's some other thing in there that's messing it up, so we might be able to say, okay, this is, one side's magnetic and we're
Okay, so
tossing it
it's
onto
all-
a metal table, so it's
all
gonna stick,
theories.
what?
It's all theory.
Well, in a way it is. Here's one thing though to understand about probabilities. Probabilities give us the chances something will happen. Okay? You're not gonna get guarantees. Okay? Unless something is literally impossible to happen or impossible not to happen, okay, you're not gonna get guarantees. Alright, we'll talk about that more later, but anyways, yes.
Well, the 1,000 like coin flip heads every time.
Mhm.
There's the same chance of that happening as you have of like it switching off between every single one. So
Yeah, that's the thing. Theoretically, any result when you're flipping a coin is equally possible. It's equally possible to get 1,000 heads as it is to get 500 heads and 500 tails. It's 1/2 to the 1,000th power. Okay, which is really small. But one of them has to happen, right? So anyways, I want to move forward here and do a couple of examples. One other way that we can determine a sample space, though, that's particularly helpful when you have a number of choices for 2 variables or 2 events, is making a table. And the most common of these is rolling 2 dice. Okay, you roll 2 dice, you're going to get a 1 through 6 on the one and a 1 through 6 on the other. Okay, so if you're adding them up, if you've ever played a board game, you've rolled 2 dice before. Okay, you're going to get a 2 or a 3 or 4 or 5 or a 6 or 7 or 8, 9, 10, 11 or 12. Okay, now that's not all the possible ways the dice can fall. There are 36 possible rolls, but that doesn't mean our sample space has 36 elements in it, okay? What would our sample space be in this case? It would be 2 through 12, okay? Yeah, not with 2 dice. So 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, again, like we had with the heads and tails one, that doesn't mean all of these are equally likely. Okay? How many ways can you roll a 2?
Why can't you roll a 1?
Because you have 2 dice.
Chris, why would you say something like that?
Word when you get it twice.
I'm sorry.
Alright, that's okay. Alright, that would be something that's a probability of 0. Okay? Rolling a 1 with 2 dice.
You just roll a dice.
There's only one way to roll a 2, right? You have to get a 1 and a 1. And there's only one way, listen please, there's only one way to roll a 12, okay? However, to get a 3, you could roll a 2 with one die and a 1 with the other, or you could roll a 1 with the first die and a 2 with the other. So there's 2 different ways, okay? There's 2 possible ways of getting a 3 or an 11, all right? Which is the most commonly rolled one,
6 or 7.
theoretically?
7.
7, okay? There are 6 different ways of rolling a 7, okay? There are only 5 ways of getting a 6 or 8. There are 4 ways of getting a 5 or 9. There are 3 ways of getting a 4 or a 10, okay? So, you see here, the probabilities are different. By the way, this is why in some board games that you are rolling dice, sometimes unique things will happen when you roll a 7. Okay? Because 7 is the most commonly, theoretically, 7 is the most commonly occurring one. Okay?
What unique things?
Like, I like playing Settlers of Catan. You ever hear that game?
Yep.
It's a cool game. You gotta look it up. It's really fun. And it's easy, well, it's not easy. It's a challenging game to learn how to play, but once you get the hang of it, and my son plays it with us, and he's in 2nd grade, so you could figure it out. But anyways, if you roll, there's a character called the Robber, and you can steal people's resources, and that you get to use that anytime you roll a 7. So they want that to happen, to kind of throw a kink in people's plans and, you know, mess up the game for somebody. So they do that. Or, well, think about how many different ways can you roll doubles?
6.
6 different ways. 1s up through 6s. So, Monopoly, if you roll doubles, you get to go again. That's going to happen 1/6 of the time, theoretically. 6 out of 36 of the rolls are doubles. That's how you get out of jail. That's how you get to roll again. Monopoly uses it too. Okay. Yeah. So, yes.
What is the first row?
Oh, hang on. Listen, please, guys. This is just how many different ways you could roll a 2, how many ways you could roll a 3. There are 5 different ways you could roll a 6, with a 5 and 1, a 4 and 2, a 3 and 3, a 2 and 4, or a 1 and a 5. Okay? So, now let's just talk through a couple of these. We won't get through all of them, but let's talk through a couple of these. If we have a coin and a 6-sided die, this is one where the table would be helpful for us, okay? So we have a coin, which means we get either heads or tails, and then we get a die, so we have 1, 2, 3, 4, 5, or 6 for ourselves, okay? So a head and a 1 or a head and a 2. Okay, that's part of our sample space. The rest of it would be a tail and a 1, a tail and a 2, a tail and a 3, 4, 5, and 6. Now we would want to list those in the braces to express it as a set, but that would be our sample space. Okay? Another case like number 3 here. A taste tester has to rank 3 varieties of orange juice. Okay? A, B, and C according to preference. So what's one way he could rank them?
CBA.
I heard ABC and I heard CBA,
ACB.
CAB.
ACB, CAB,
ACDC.
BCA. Ooh, that's
BCA.
What's that commercial for college?
Do we have them all yet? No? There's one more.
BAC.
BAC? Yeah, there we go. Now guys, think about this please. What are we really doing here?
3 by 3.
What do you mean?
Rearranging the
Combination of
letters.
3, like, you have 3 things being A, B, C, and 3 different options, like, you like A the most, B the most, or C the most. Or it could be
Okay.
anything, so it's just 3 by 3.
Yes, and what did you say, Nick?
Permutation.
It's a permutation. We're finding all the permutations of 3 items, A, B, and C. Here, this is a case where a sample space, the order matters, okay? Because if it didn't, we'd only have one thing, because we're using the same 3 every time, okay? Two marbles are selected without replacement from a sack containing 2 reds, 2 blues, and 1 yellow. The color of each one is recorded. So if I'm picking 2 out of there, what could I get?
2 reds.
2 red, 2 blue.
2 reds, 2 blues. Could I get 2 yellows? No.
Red and a blue,
A red and a blue,
Yellow and blue.
a yellow and a blue,
and a red and a yellow.
and a red and a yellow. Okay? So look, there's our sample space. There's only 5 possible outcomes. Okay? Alright. Now, number 5, think about this one. 2 county supervisors are selected from 5 supervisors. Okay? What are we really, if I wanted to figure out how many I could have, it's a combination. Okay? 5 choose 2 would be my combination. Alright? There wouldn't be a ton of them, but more than I want to list right now. Okay? So, that's the idea here behind finding a sample space. Okay? Tomorrow we're going to look at calculating actual probabilities once we know what our sample space is. Okay? Alright.
Can I take my test, please?